Welcome back. At this point, what we've managed to do with our formulation of the finite element method for these 1D linear elliptic PDEs is actually state the problem in completeness, right? We've derived the matrix vector equations for linear and quadratic basis functions explicitly, and we've also laid out the path to be followed when we go to higher order basis functions. And while in the formulations we developed, we carried out analytic integrations of all the terms that were needed. We've also looked at how we would go about carrying out numerical quadrature, right? Numerical integration. And numerical integration is what would actually be done in a code which before too long you will also be writing. What I'd like to do now is actually observe that we are ready to move on to other problems, right? We're now ready to move on to multidimensional problems. Before we do that, however, it's important to understand a little more, just a little more about the mathematical basis of the finite element method. And there are at least two things we need to do. What we will start doing with this segment, and it'll take 3 or 4 segments or maybe a little longer, what we will do is to understand why the finite element method works, what its special properties are, and also get a fairly high-level view of the way finite element convergence works, right? And we'll see the mathematical basis to this. We'll see a few simple proofs for why the method works, okay? All right, so that's the plan. We are going to start by talking of norms. Okay, and by this we mean mathematical norms, right? How do we estimate the, so to speak, the magnitude of certain functions, okay, in a manner that makes sense for what we have to do here. Okay, let me give you a little background before we really plunge into this subject, and let us start by considering the following, right? Consider the finite dimensional trial solution that we are working with, okay? So consider the finite dimensional trial solution. Okay, UH. One thing I'm going to start doing from now on is perhaps stop referring to this as the finite dimensional trial solution, though it is that, but actually start calling it the finite element solution, okay? And so this is the field that we would get by carrying out the finite element solution and maybe going back and reinterpolating from the trial solution degrees of freedom, okay? So let me also state that. Also called the finite element solution. Okay? That's probably how I will refer to it from as we move on. All right. We'll consider it in the context of the problem we're solving. So we have something like that. And let's suppose we have some number of elements here. Okay, what I'm going to do is consider, to show that there is some generality, I mean complete generality with what I want to state, let's consider that we are using here quadratic basis functions, okay? So that would mean what I'd intended to be elements here, each of them has mid-side nodes, okay? So this now is omega 1, right? That represents some general element omega e. Right. I'm going to now sketch out the quadratic basis functions. All right. So we have that, we have N2, and I'm sorry, it's sort of strayed over a little. Let me try to do better. We have N2 and we have N3, right, for this element. Okay, I'm not going, well, let me label them just for this one maybe. N1, N2, and N3. Okay. For element 2, let me perhaps use a different color so we can highlight a certain point. Okay, so for element 2, my my basis functions are going to be that. Okay, I can do better than that. Sorry. Okay, that's N1 for element 2. That is N2 for element 2, and that is N3. Okay, so again I'll say N1, N2, N3. Okay, now of course we also know that associated with each of these nodal points we get trial solution degree of freedom values, right? So let me write those, and here I'm going to write them using global numbering. Okay, so here I have D1, I have D2 here. I realize I switched from sub to superscripts in the first one. Okay, D1, D2, I'm going to write D3 here, D4, D5, and so on. Okay. Now, the point I'm trying to make here is that the way we would construct our field UH now, right? UH within each element E would be obtained by that process, right? DAE, and we know how to go between local and global degree of freedom numbers. Okay. Observe the nature of our basis functions here. I'm going to ask you a question. What I've sketched here in red and green are the basis functions respectively for elements 1 and 2. Is the solution UH continuous? So the solution, the finite element solution that one would generate by reinterpolating from the trial solution degrees of freedom, would that be continuous? Right, think about it. The answer is yes, it is continuous. Okay. Mathematical notation for a continuous function is C0 on omega. Okay, when we say a function is C0 on omega, we're saying C0 simply means the function itself is continuous, right, over the domain omega. Okay, what about its derivatives? Are the function UH, are its derivatives continuous over omega? Think about that. Well, let me ask you in steps now. UH comma X. It turns out that it is continuous within each element. Right? So if I look at UHE comma X, right, restricted to a single element, right, within that element E, the derivative is also continuous. Okay? So we would say that this function is C0 on omega E. Right? So the derivative is continuous within each element, right? What about over the entire domain? Is the derivative continuous across the domain? In general, well, not in general, the derivative indeed is not continuous across the domain. In particular, there are points of discontinuity in the derivatives, right? At element edges, like there and there, right? What we will see is that UH comma X is discontinuous. Okay? All right? So UH comma X is discontinuous in all of omega, right? So now here what I'm specifying is that we're not considering UH restricted to a single element, right? It is across elements, okay? So it's discontinuous in omega, and so what we say, however, is that UH comma X, the derivative, is not in C0 when we take the entire domain omega into consideration. Okay, so this is an important thing to notice, right? And where does this come from? Why is it that the solution UH, right, the finite element solution, is itself continuous, but its derivatives, when considered over the entire domain omega, are discontinuous? Where does that come from? Right, it comes from the basis functions, right? So what's important to notice here is that the Lagrange polynomial basis functions have been constructed to be only C0 on omega, right? We have basis functions which are only continuous, and that's immediately observable if you just look at this sketch that I made of the basis functions, right? Clearly the basis functions are continuous, but of course if you look at the inter-element nodes, it's clear that the derivatives are not going to be continuous. And of course, once you have that, any function that you then construct using that basis to represent the function is also going to be only continuous, but not be continuous in its derivatives, okay? So we say that it's only C0. We say that it is not the function itself now, the function UH, the basis functions themselves are not Cn on omega for n greater than 1, n greater than 0. Okay? Right, the basis functions themselves have been constructed to only be continuous. They're C0. Okay? Their derivatives are not continuous. Okay? Right? If their derivatives were continuous, we would say the functions would be Cn, right, where n would be the number of derivatives that were continuous. Okay, so we're saying that the basis functions are not Cn, they're only C0. Okay? All right? So let me just give you an additional statement here to give you the more general case. In general, a function is in Cn omega if its derivatives up to order n are continuous on omega. All right? Our basis functions themselves are continuous. None of their derivatives are continuous. Therefore, they are only C0. Okay? The 0 indicates no derivative continuity. Okay? However, Remember when we talked about spaces, we introduced these spaces L2 and H1. Okay? So, however, does UH, right, the finite element solution, belong to H1 on omega? Okay? Right? Remember, so what we're asking is, what this means is, if you recall, is the following. If we integrate over omega UH square plus 1 over measure of omega to the power 1 over number of spatial dimensions, okay? Sorry, this should be 2 over number of spatial dimensions. Okay, times UH comma X square dx, right? If we do this, okay, what we're asking is this quantity bounded? Think about it. UH is not continuous, okay? So, what we will find is that this term, right, the derivative term is discontinuous. However, if we integrate it, right, discontinuities are not unintegrable, right? They can be integrated. Okay, so when we integrate it, we will see that this quantity that we put down here on the left-hand side is indeed bounded. Okay, so the answer is yes. Okay, right, so even these discontinuities themselves don't pose a problem. Okay, all right. Now, okay, so UH does belong in H1. Okay, so I'm going to use this background to say that, and of course, you know, of course UH belongs in H1 because that's how we constructed UH, right? Remember when we defined SH, right? Okay, so recall UH belongs to SH, which consists of, we said that it consists of all functions UH belonging to H1, right, on omega. And then we put in boundary conditions and so on, right? So by construction, it does belong to H1, and I'm just pointing out that, yes, it does indeed belong to H1. Okay, with this as background, I'm going to start defining some norms.